In DSP, you can use MATLAB to do the demos, the design, and simulation. But you can also use some other programming languages. And one of the interesting one that I normally use is Python. And in today's session, I'm going to show you how we can also use Python to do the demos. Instead of MATLAB, remember MATLAB, you have to install it, and sometimes you need a licensed version that costs a lot of money, but Python is an open source, and you can either download and install packages or can use an online platform. And the online platform we're going to use is Google Colab. I know some of you know the Google Colab already. So if you don't know, then you search for it. You say Google Colab. It is Google Collaboratory. This is the platform where you can. Yes, so it is. You can click on this link, and then it will be shown like this. And yeah, you can open a notebook, or you can use the existing one. Okay, let me go to. I had one that I was using, but you can just click on open new. Let me see. Yes. So this is my platform. I hope it is visible and clear. Please confirm.
Yeah, it is visible.
Perfect. So we have this normally here. You find unknown or unnamed. So what you do, you name it. Me, I've named it DSP practical session. I can say practical session 1. You can give it a name. And it has tabs that you can use, but mostly for us, we're interested in code. Okay. We are interested in code, and you can just click on code. Okay. And then it will come here. Click on code, and then a window will open where you type your code like this. But let me expand it a little bit more. That is too big. Now, with Python, like I said, you can just import. It has some functions or packages that you can use to do your work. And in DSP, the most important package that we normally use is NumPy. NumPy is the numerical computation package that you can use to do most of the. It has mostly the functions we use in math. So you can get the sine, the cosine, you can get the pi, you can get most of the functions we use in mathematics, you can get them from NumPy. So the first thing to do is to import some of those packages that you want to use and also to know them. Then the second package that we use is the one for plotting, because at the end of the day, when you do your design and you want to simulate something, you need to plot and see the visual aspect of whatever you're doing. Okay, so I will import the packages and then demo. So you use the import keyword, and you can see how it is highlighted, and then you say NumPy, and you can import it as you use an alias so that you don't continue typing NumPy, but you can just use NP. That's the standard, but you can use any other symbol that you want. So now this means every time you want to use NumPy, you can just type NP. Then you put a dot, then you type your function. Okay. Then the other package I said it is matplot. Matplotlib and you can see the beauty with these online platforms, there's AI embedded and it can give you suggestions of the code. Okay, and you can just press the tab. Okay, but I don't want all these. It has imported most of them, but I need it only this. So you see it is matplotlib.pyplot, and instead of typing the whole of this one, you just say you use AS, an alias, and you say purity. So we shall be using purity. And this is for plotting the signals. I think for now, these are the only two that we need. Okay, for now. And then you can use a hash to type a comment, and this comment is not executed. You have done programming and you know comments. So here we are going to say we have our signal, we can call it Y, is given by sign. For example, it is sign 2, it's sign 2 pi, okay, 2 pi ft. Okay, I'm just typing it like this. Yes, some symbols I might not, but I can just put times 2 pi ft. Just like this. So we have this signal that we need to visualize. Okay, so that is a comment. You can see how it is highlighted in green, whatever. So the first thing to do, this is the only thing we are given. So they're like plot and visualize this signal, which is Y is equal to sine of 2 pi ft. And this is a time, it is a continuous signal, a sine signal. So the first thing to do, and here they will be like given f equaling to, they give you frequency, for example, 10, 2 pi ft. They give you the frequency. So once you have that t, the frequency, then you can start by getting what you need to plot. First and foremost, before you plot, you need to have the x and y, or the horizontal and vertical axis. So on the horizontal, we plot the time range, and we can say, time will be given by, we can use np, which is our package, dot, yeah, it is suggesting that I can press tab. Okay, you see how it is suggesting the code. So, and it has known that this was, you can see from our comment, it has just generated the code. So you can use line spacing, line space 0 to 1, but for 1,000 samples, and this is very good. So you can use np.line space 0, 1, then 1,000, like this, the way it has suggested. And then you can plot your signal, which is y is equal to np dot 2 times. Now, instead of typing pi like this, you type np.pi, because that pi function will be in numpy, 10 times ft. But because we are given f as 10, instead of typing it like this, you can say f is equal to 10. Okay, then here, instead of putting 10, you put f. These are variables, and you know how to type variables. Okay, and that's it. So now we have that, and then we can now plot. Now, since we have these two, we can plot the signal. And to plot, you use purity dot plot. Okay, the way it is suggesting, by the way. Purity dot plot. These ones I can first leave it, but we shall use some of these ones. So purity is the matplotlib, this one. Then plot is a function for plotting, and then you put a t which is your time scale, and also the signal which you're plotting. And once everything is done like this, you can press here to run code. Just click run. So once you run, this becomes your signal. As you can see, let me minimize code. Yes, this becomes your signal. It's a sine signal like this, like this, like this. So I hope you're able to see it, visualize it. But now this one, we need to give it labels. Okay, we need to label this horizontal axis and also the y-axis. So to label them, it's again label them before you plot. Then give what we call xnp dot x label. Okay, and just put x label. Let's see. X label, purity.x label, then inside you put the time. This is the time in seconds, for example, and y label is the y, the signal, which is equal to, yeah, I can give it like that if I want. And then you can give it a title. And this is amplitude. You can just put amplitude. Amplitude. Okay. And this title, this is the title. So I can leave it like that. But I put 2 pi ft. That is the title. We are plotting that signal, and or you can say, yeah, signal. So like that, you can just click play again or to run again, and then you'll have your title, your amplitude, and the time. Okay, so this is how we can plot the signal. This is just a simple demo of how you can plot that signal. So are we together? Is the code visible and is the signal visible too? I need your confirmation to know that you're following as well. Yeah, you can give me a thumbs up or just unmute and say, yes, we are seeing and we are following.
Yeah, we are seeing and following.
Okay, perfect. So now that we have demonstrated that, you can also demo. This is a sine signal. You can sometimes also plot a square signal, but normally we deal with sinusoidal signals. So in case they ask you to plot a square signal, you can use a technique. There are two techniques. You can either use the sign. You change the sign of this sign signal. As you plot, you keep changing the sign, and then it will plot. Instead of plotting like this continuous, it will just plot zeros and ones. Okay, on and off, on and off, on and off, on and off. Let me show you. So suppose we wanted to plot. Yeah. Let me remove this one. Yes, I will say plot a square wave. Square wave signal. Wave signal. So I will just simply say that y is equal to, I will say sine. I've used np dot sine. Okay, this is for changing the and I can just place, yeah, like this. np.sign, then np.sign. Okay, so here you put the sine wave here inside, and then outside you multiply by the sine function, convert it to a square wave, and then you can plot. Let me see if it can work. Just plot like that. Yes, perfect. You see it? So it is from the sine wave that we change into a square wave by just multiplying it by the sine function. Yeah. So instead of continuing, it will be plotting on and off, on and off. So it will be continuous, but on and off. Okay, like that. Or instead of using the sine, now this is method 1. The method 2, by the way, now this one you can say hash, just comment it out. Then you can say going to here up, you can import another package, and this package is called SkyPy. From you can say from import, you can say from this package import signal. So we can use the signal, and in fact in DSP you need to know this package here. So import the signal. We're going to use now this signal. Okay, now here, instead of that y, we're going to say y is equal to signal. Okay, signal dot square. Yeah, we just get the square function. From that, and then I can press tab. Yes, 2 times np pi times f. They are like that. So instead of using the sine function, we just use the signal dot square. Then you can plot. Let me see. Yeah, you see, still get the same thing. Yeah, still get the same thing. Yeah, so this is the first one. Is there any question or comment, something that you want to understand, because you're going to practice some of this? If you have any question or comment, you can, before we move to the next. So how do you see it? Just one member can unmute and tell me that everything is still fine and following, and can practice this afterwards. Anyone? Yeah, so I hope you're still following. Now, you can insert another code platform. Now this is one. If you don't want to delete this one, you can insert another one. And I'm going to say code. Okay, so this one would stay up, and I can insert another one. Now this one, we still need to import those packages, because now we have moved into another cell. We call it cells. So you can import. Because here you'll be learning as we import these things. Import numpy, I can just place place. Yeah. Import numpy. Yeah, I can just import like that. Numpy as np, then import matplotlib dot pyplot as plot. Now here we are going to demonstrate plotting a discrete signal. Now we have been plotting continuous signals. Now we can plot. Let me first. Yes, we can plot a discrete signal. And let's say we wanted to plot the same signal, which is y is equal to sine of 2 pi ft. Given f, said it was equal to 10. Yeah, 10 has. Okay. Yeah. And we can say 10 has and also sampled, because now we want to sample that signal. We can say sampled at 20 hertz, for example. Yeah, remember, it has to be more than this. We assume this is the maximum frequency within this signal, and this one has to be at least twice. But now we are saying let's sample at 20 hertz, for example. So we shall still, now here you need to get your T, your time samples. Okay, you can call it TS is equal to, now instead of np.line space, we are going to use another package which is arrange. Now line space, for it will specify the spacing depending on how many samples you've specified. But in sampling, we don't need this because we need equal sampling, okay, equal sizes. Now we use a range so that we specify our own range. This is another function that you can use. And then we can say from maybe 0, yeah, to 1. 1 is like a second. So in between is how many seconds do you want to sample? But you can sample within, for example, half a second, because you don't want to have a wider range. You want to view your signal. If you sample in 1 second, you might not, or 10 seconds, might not see it properly. Okay, I will demo. Then instead of now here it is from this 0 up to 0.5. This is second, and the interval is now the period, and which period is 1 by fs. But before that, fs, we need to put fs here. Shall say fs is equal to 20. Okay, even our frequency that we had, but that one we might not need it. So fs, now this is the period. If you want, you can say ts, capital ts, which is the period, is equal to 1 over fs. We did this in class. And instead of putting 1 over fs here, you put ts. So this is the time interval or the period. So this is what you put here. And then, as usual, you can now plot your y signal. Yeah, as it is. np.sine to n pi times f times ts. And remember the way we used ts, which is nts. So this ts here involves this period. And now you substitute it here. Okay. Instead of t, use ts, nts. Remember? So yes, now we can plot the ts times that. But instead of plotting like this, let me first plot. You'll see it will be continuous. Can plot, but you see how it is very fun. I think it's because of this, but we don't need that. Now we have sampled. What we need is to stem through. Stem through. Use the stem instead of plot. Yeah. So this stem, now it plots it as a discrete sequence. Wow. You see that? Yeah. So this is our signal sampled at 20 Hertz, and these are the samples. As you can see, you can even trace the signal again if you wanted. You can trace the signal. And now you can still put the X label, the Y label, 0T.X label, and label your, yeah, and place, yeah, your time, your amplitude. Now here, this is sampled signal. For the signal. And this is it. And this is a discrete signal. And if, yeah, sampled signal, amplitude, and then time, like this. And you can see how easy it is to do practice in Python to visualize some of those signals. And from here, we can also demonstrate what we did in class. When you're doing sampling and you're converting a time signal into a discrete signal. Okay, so you have to understand some of these techniques. Now you can relate when you go back to doing computation. Okay, so that is the second one. Now let's if there's no any question, I hope you're still following. Now let's go. Let's look for another. Now here we're going to do the actual. Now this was just a demo. We are going to do the actual sampling of a signal. We're going to look at the signal. We plot it alongside the sampled signal so that we view them together, and then we can compare and see. We can compare and see. So this is what I wanted to show you. Now this is half a second. If you use the second, for example, you can see, yes, actually this is better. This is better. You can see it well. Or if you use 10 up to 10, you see how it will. Now this is interesting, and you can tell if this is a signal. See? So you can keep increasing this one to play around with to see. Now if we put 100, you'll be so close to each other, and yes, you see, and you've seen some of these signals, and the signals are like this, by the way. Instead of viewing them as it's a sinusoidal wave, sometimes there are so many samples in between, and this is how signals are. But because we want to visualize and also tell that it is from, yeah, so you can plot like this one. Yeah, perfect. So let's move to the next. If you have any comment, any question, you can raise it before we move to the next. I can see we are now 26. Yes, this is some good number. Someone is attending with face. Face, what happened to your smartphone or device? Anyway, so let's move, because after now these sessions, they will be less than an hour. We are not going to be taking long. It will be less than an hour. Then for the next 1 hour, you can do your practice, okay, in groups or even individually if you want to practice individually. But I prefer groups so that you discuss and understand. So now here we have our signal. Let me start with the comment. We have our signal, and it is x of t x of t equaling to 3 cos 100 pi 100 times pi t. Yeah. So this is the signal we have, and they're saying it is sampled. Signal is sampled at the rate of sampled at fs. Now, who can tell me if you had a signal like this one, what is the minimum sampling frequency we can have? For example, if it is not given, just unmute and tell me.
100.
Sorry? 100?
100.
Yes, yes, perfect. Who is that?
Timothy.
Yes, 100, yes. Because this is 2 pi, and now 2 pi f. Now this f means it is twice, okay? So it is 50 Hz. And according to Nyquist theorem, you're supposed to sample at a frequency greater than 2f or equal to 2f. 2f where f is maximum. So 2 times 50 is 100. So 100 will be the minimum. But then it is not recommended to sample at the minimum. And we shall see. So you can choose a higher value, which is 200 Hz. Perfect. So from here, then we can still import our packages. Someone wanted to ask a question?
Yes, I have a question.
Yes.
If I find that the minimum frequency is like 90, after you have not specified, can someone use a higher frequency to do the calculation?
Yes.
Like 100.
Yes, if you find you have 90 as this frequency specified, and they have not specified the sampling frequency to use, so you use the Nyquist theorem, and you get that frequency at least double that frequency. You can use that. If you had 90, then you can use like 180 plus 180 Hz or 200 or whatever. It has to be higher than at least twice the frequency identified. Is that okay?
Okay.
Yeah.
Yes.
Okay. So we have imported our packages. 2 of them, these are the main ones, and then we are going to plot the continuous signal. Continuous signal. Okay, and then we can say T is T equaling to NP dot. Here we said we can use line space so that it spaces itself. Since it is just a continuous signal, then we say from 0, can say maybe to, yeah, 5 milliseconds up to 1,000 samples. But you can specify any range you want. And then you can say your X key. You can either do it like that. Don't put brackets like this. They will interpret it differently. You can either put X alone or XT or X underscore T. So it will be equal to 3. Now we plot this signal the way it is. So it is 3 times. 3 times. If you want, you can put spacing, by the way. Let me try. Times cos. Now it is cos of 100. It's 100 times np.py, then times t. Okay, or t specified times t, like that. And then you can, yeah. So that is one. We are going to first not plot it, because we wanted to plot it together with the sampled signal. Now I'm going to put here a comment and say sampled signal. So now the sampled signal, how we plot it, we first of all identify fs. By the way, this AI, the AI embedded within this platform is good. Now, when you put a cursor without even typing, it is saying we first put fs, and it gets it from the comment here we put. You see? So I can just say fs is equal to 200, which is okay. And then I can specify the time period. Yes, it was specifying. Oh my God. But it's good to know what you're doing. Don't rely. Yeah. So like that. And then you can also specify your time. Okay, but this is now the sample time. Actually, you can use n for the sample. Since we want it discrete, you can say n instead of t. Yeah. N is equal to np dot arrange. Yes. I can say np dot, now I use arrange because it is sample, I need equal. Then I can say from 0 to, for example, can use the same 0.05. Then you can say ts here, the time interval. So this is the sampled time interval. And then we can say now x. Now instead of xt, we can say xn. Okay. Wrote this one. Xn is equal to 3. Yeah, it is specifying by the, I can use 3 times np. Yeah, like that. Needed to see if when you give spacing, does it work? Yeah, I want to see in here. This is beautifying the code, but has no effect. So now that I have that, I can plot. Now plot, I need to plot both of them together, the continuous signal, then the sample, so that you can see. So here I will say period t dot figure. I will use the keyword figure, then specify the size that I want. So fig size, yeah, you can place. This one you learn also, so you can specify the figure, the size that you want, so that you control how it will display. So I need, this is horizontal and vertical. The way it is horizontal up to 10, vertical up to 5. But normally the recommended one is 12 and 6. We shall see the difference. Then you can now plot PRT dot plot. For a continuous signal, we use plot. So I say plot, and I can use tab, just complete. And here it will be T. Okay, I'm plotting this T, then XT. Wow, has given me, yeah, a clear one, which is a continuous signal. Yes, perfect. So here, now I'm going to plot the sampled signal, which is stem. Yeah, it is also suggesting this is good. Purity.stem, then now I use this. It has given me a clear plot, a sample signal, but here I can also specify. I want to specify the color. I need to change color so that it is identified. So I will say line format. Line format. Yes, this one. Line format is equal to red. Yeah, I can use arrow like this, continuous. Then I mark it with the 0 so that we see the sample. I mark it with this O. We see the sample. Yeah, think like that. So these ones, they are extra. You can learn. These are formatting, line format. Okay. You can also use base format. Let us first use that one alone. And then you can put the labels. Okay. Time label, amplitude, continuous. Yeah, it is both continuous and also sampled signal. How does it know that I wanted to put that? Then you can also hierarchy grid so that you see the lines and then show. Okay, so this is a clear code. If we have no errors, then it should run, and then we should be able to see a continuous signal alongside a sampled signal. Inside the sampled signal. So let me plot if everything is okay. Wow. I don't know, you guys, whether you can see this one. You see it? Even be minimized so that you can see the whole of it. How beautiful is that? Guys, if you can see, just tell me what you're seeing and how beautiful that looks like. I hope you're awake. Now I need the lady to unmute and tell me. Call the names. Yes, Ashemire. Tell me. Go ahead. I think you're muted. Can't hear you.
It's beautiful the way it is represented.
Okay, great. I just wanted to hear that. Yes. Okay, great. So the way it is represented, as you can see, this is a cosine. You see, this one is a cosine. Now it is sampled. These are samples. So you can see it is sampled here on top, sampled here, the crossing, sampled here, at the minimum, sampled here, sampled here, sampled here. So this is the signal we have and it is sampled. So what we do, if, for example, our frequency, because you need to play around with some of these, if our frequency, sampling frequency is not 200, for example, if we sample at exactly 100, okay, at the increased rate, I can, where is the face? Here. I can change it to 100. So when you do practice, you'll be changing some of these frequencies and also the range to see the difference. And I can click plot. You see here, now it is still. Is there anyone who notices the difference? When you sample at 200 and when you sample at 100? Unmute and tell me if anyone has noticed a difference between the first one and this one. Or if it is the same, you can still tell me.
From what I say in this one, the samples are less
Yes,
than the other one.
absolutely. The samples are less. And can you remember where the sample was? Those samples that are missing here?
They were at the
At zero
horizontal
crossing.
line where
Ah, absolutely. Now, when you go back to reading your notes, you realize they will say if you sample at exactly the Nyquist rate, at exactly the frequency, the times 2 frequency, then there will be a problem of reconstructing your signal because you'll miss those crossing points. You find the crossing point errors. Now here, before we had a sample here, which was marked at the crossing point. So this will help you when you're reconstructing. Now this one, you may not tell where this is passing by. Okay, let me put back. Some of you might have missed because I want you to learn as we do this. Okay, so let me put 200 again, and so that you see, now these ones were missing at the exact Nyquist rate. You are missing, but now with these ones, now you can tell because it has the maximum, the crossing, and the minimum. And this one you can reconstruct because you estimate and be like, okay, this is the cosine when you trace, and then you can construct your signal very well. Okay, if I put back at 100, then you see those missing. See, these are missing. Now, let's also continue to sample at a very low rate. Okay, 50. Exactly the frequency we are given. This sample, which is 100 divided by 2, which is 50. If we sampled at that frequency, not higher, what happened? So now tell me, who can tell me the difference? See the difference? Tell me, and the samples continue to shrink. Okay, anyone to unmute apart from Timothy and the Asheria? Who? I want someone else. And you mention your name so that you get to the bonus point. Anyone? Just unmute. We have so many people here. Don't tell me that you can't unmute and say something. But from Ashemire, China, and Timothy. Mkwenda kufuna point session. The question is that we have now sampled at 50 Hz. So tell me the difference you see when you sample at 100, when you sample at 200, and when you sample at 50 Hz. Tell me the difference you see in this signal here of ours. Okay, if they are fearing, then Timothy and Shina, you can still hear me.
I think from
Your name?
it's a diagram. I'm just trying from.
Yes, you try. There's nothing like
Okay,
wrong or right answers. Just try you. Yeah.
I'm trying, but I'm speaking from the theory bit of it.
Yeah.
I think when you sample at a very low frequency, there's distortion and aliasing that will happen to the signal.
Mm.
Yeah.
Yeah. So based on what you see that one happening, especially when you're trying to reconstruct the signal, the later stage. from the practical point of view? Based on what you see, Agure, tell me.
Yeah, when you changed it to 50, it tended to be distorted.
Yeah. Yeah. Okay. Anyone else to continue building on Agure's theoretical explanation?
Can I say something?
Yes.
So I feel like when you're reconstructing the signal, it's like as if it will give you a straight line instead of the analog, the continuous signal. Yes. So it has less samples.
Yeah. Okay. Anyone else?
It has less samples.
Yeah. Thank you for that. Anyone else?
Yes, good afternoon, sir.
Yes. Good afternoon. Go ahead.
According to my observation, when we sampled at 200, we have all the samples in both sides, in positive and in maximum amplitude, with maximum amplitude and minimum amplitude. Then when we sampled at 100 at exact frequency, we saw at x-axis we missed some point. Then after sampling at 50, we are seeing only samples appearing on maximum amplitude and maximum amplitude. Then on x-axis and minimum side, we are losing points. So the signal will be distorted.
When you're reconstructing, yes, very good. So he has explained it very well. The signal will be distorted because you'll miss out. First and foremost, you'll miss out the crossing points, the zero crossing points, and also miss out the negative or the minimum point. So you might not tell, and you might reconstruct the wrong signal. So that is the distortion Agure was talking about as well. Perfect. So this is the kind of explanation that I want you now to have and to understand now. And remember, this was our 50, because this is 2 pi that is embedded in here. 2 pi, which is 100 divided by 2, it is 50. Now, how about if we put at 25? Okay, at the even below the maximum frequency. Okay, so now if you see what is happening now, even this sample has disappeared, and now we have this first sample and the last sample maximum. And now you're going to miss these in between, you see? Yeah, and also the negative bit and also the crossing points. So you need to be playing around with this one. Now, if we put back at our sampling frequency that we had, then you have most of the samples to reconstruct. Yeah, as long as you have this maximum, you have the crossing, you have the minimum, you have this, then you can reconstruct at the end. That's why higher is better. And even better if we put it at 500. You have more samples, minimize, because even here in between, as you reconstruct like this, you might bring the curve maybe not exactly here or maybe somewhere. So let's put at 500 and you can say, you see? Perfect. Now this is even more beautiful. You see it? Do you think this one is very easy for you? Even if it was manual reconstruction, this one is easier to reconstruct than the previous one, because you have several samples in between that you can trace. Okay? Yeah, so when you play around with this will be interesting on your side, and you can later, if you want, you can print this one or crop it, and it becomes your screensaver on your desktops. And your girlfriends and boyfriends from the upper campus will be asking you, oh my God, how did you draw this beautiful? You'll be like, okay, Don't you know that I'm an engineer? Yeah, so this is good, as you can see. And this is how we are sampling in class. You are putting those sampling. So this is quantization. Now you sample, quantize, and then you can code. You code these values. Then you can have your signal. Okay. And if you want, then this you can remove it. You can remove. It's continuous. You can put hash. Maybe you can hash it. This one. Then when I plot, yes, you see, when I plot, then I will have only the discrete. And you can tell that this is a cosine function. And from here, with all these points, you can surely construct your initial signal.